Hello everyone and welcome to this Know-How Solutions webinar. My name is Björn Skjonberg and I work as Field Application Engineer here at Know-How Solutions. So this is session 2, maximize your development with Keil ULINKpro. So session 1 was yesterday. I gave you an overview of Keil. I shared with you the news in Keil, so both Microvision, what's new there, the new compiler, ARM Compiler 6, and also that there's a new debugger, Ulink Plus. Then I showed you a hands-on demo on what you need to get started, and also where you can collect the different pieces of software that you need. So this webinar was recorded and should be on YouTube, so you can watch it again. Today, session 2, I will talk about debug. I will talk about trace, so both ITM and ETM, a little bit on the RTOS awareness that you have with Macrocell. Then I will show you a hands-on demo with debug and trace, so when you have the different availability to the different Coresight blocks, what types of view can you get in Macrocell. Then I will talk a little bit about a news in Macrocell which is called the event recorder. So I will give you a hands-on demo for the event recorder, so both showing how the pre-made events look that are available in the MDK middleware, but also quickly showing you how you can create your own events and make benefit of the event recorder. And then I will end with the Q&A. So if you have any questions during the webinar, please write them in the chat box and I will answer them at the end. Okay, so let's talk debug and trace. So this is the Coresight that is involved when it comes to debug and trace. So this is part of the ARM IP. So your Cortex MCU has a few of these or all of these. So if we start talking about debug, so debug or level 1 as I like to call it, here you interface your Coresight via the JTAG, which is a 20-pin interface, or a serial wire debug, which is a 2-pin interface. Then you can control the run control block, the breakpoint unit, and the memory access unit. So with this access, you can, well, stop and single step your CPU, read and write the memory, so registers, peripherals, variables, and so on. You can put breakpoints, and you can download and verify the flash. So if we go up one step, so Coresight for the debug and trace level 2. So to interface this Coresight, we need a serial wire viewer. So this is part of the 10-pin Cortex debugger that has the 2-pin for debug, so serial wire debug clock and serial wire debug input output, but then you also have the serial wire output. So with this you can interface the data watch point and trace unit and also the instrumentation trace Macrocell. So this data trace will give you the possibility to sample the program counter, to get event counter CPU cycle statistics. You can see in time when the exception and interrupt is handling. And then you also have the ITM. So the ITM is kind of a system trace. So the ITM provides you with communication channels. So it has 32 channels and 2 of them has already been predefined. So for ITM channel 0 is defined as a input and output for printf style messages. So instead of using a UART to give input and output to your microcontroller, you can use the ETM channel 0 to pass the messages over the debugger and then into your debug GUI. ETM channel 31 is also predefined, and the RTX RTOS is using this to tell which task is currently executing. So when a task switch is happening, the ID of the new task will be sent out over the ETM channel 31, and this will give us very detailed timing statistics of how the different tasks are executing in your RTOS, but also if you have any blocking or things like this. So the other channels, so channel 1 to 30, you are free to define and use as you would like. So this is up to you to define and use. So if we go one step up and we go to debug and trace, level 3, I like to call it. So in this level, we have access to the ETM, so the embedded trace macrocell. And this will provide us with instruction trace. So to access this Coresight block, you need to have the debug pins, so the 2 pins debug, and you need 4 pins for trace data. So with this we have instruction trace, so this will tell you every instruction that has been executed and also detailed how long time it took for each both C code or C++ code line, but also down to the assembly line. So this will give you, well, analysis of the execution history. It will also give you the code coverage, so which instruction has been taken and which instruction has not been taken. So you can see the paths of how your system is going, so to speak. You also get the instruction on if an if statement has been executed or not. So you can see which condition has been executed, and also you can see if a condition has only been true, so executed, or only been false. So both. So you get both. So with this, you can get performance analysis. So you see how much time you spend in each function, but you also see how much time you spend in the idle function. So you get kind of a measurement of how much load are you putting to your MCU. So if you are spending, for instance, only 10% in the idle loop, you perhaps need to start thinking about switching to a more powerful MCU. Also, you see how long each function take and how much time you spend in each function. So application optimization is quite easy, because you will know where you need to start thinking more about the algorithms that you have programmed. So the connectors that are available typically on a Cortex-M device is either the little bit older, so the ARM JTAG 20 pin, and this will give you level 1, so only debug possibilities. There is a smaller version which is called the Cortex Debug, and this will give you level 1 and 2 debug and trace. So, and then we have, of course, the Cortex Debug plus the ETM connector, so this will give you level 1, 2, and 3 debug and trace. So if we have a look at the Ulink family, so for those of you who are looking to have instruction trace, ULINKpro is the only choice. But so for level 3 debug and trace, you must use the ULINKpro. But if you would like to use the level 1 and level 2, you can use any of the debug probes available. But be aware that the trace streaming is faster for the better debug probes. So the more things you would like to trace, the more trace messages that your MCU creates, the higher the load will be, and also the higher the risk of FIFO overflow, so the trace being lost will be. So you have to take this into consideration when you choose what debug probe you are going to use. So for the first hands-on with debug and trace, I'm using the same setup as I had yesterday. So I have the MCB STM32F400 board from Keil, Cortex-M4 from ST, and I have a ULINKpro. So I'm interfacing this so it has instruction trace available, and I have the Cortex-M and the ETM debug connector, so I can go level 1, level 2, and level 3. So let's show you this. So first of all, I also would like to say that I'm using the stack usage watermark for the Keil RTX, so it helps me when I'm giving memory to each thread. So this is quite simple tick box. You only tick, and then you will see the maximum stack usage. So I will show you this in a debugger in a few seconds. So I need to go to options for targets. I need to go debug. So I'm using the ULINKpro. I say settings. I see that I can read out the ID of the MCU I'm supposed to debug. And trace is turned off. Okay, let's go. So we enter debug mode. And we see now. So we have the disassembly view. So we have stopped at the first instruction in main. I can have a look at my registers, and I can of course step my code, step over, step out, and so on, as you would expect. I can put breakpoint. So if I put a breakpoint in the dark gray area, because this is where code is being executed, light gray area we have no code executing, and I click run, I will hit that breakpoint, as you would expect. If we run a little bit and then we stop, like this, you see here in the system and thread viewer, I get an overview of my RTOS. So I have 5 user-defined threads, and I have the idle daemon and the OS timer thread. I can see which state my threads are in and how much delay they are, if they have a delay. I can also see the stack usage. So I see the current stack usage, and because I enabled the stack usage watermark, I can also see how much the maximum stack usage. So I see that the maximum is 392 bytes out of 1K. So I have perhaps in this example giving my stacks a little bit too much memory. I also have an overview of my peripherals, and I have the default peripherals available here. So this is pre-made from Keil, so this is not something you have to do yourself. So if you have your own custom peripheral, which you have developed, then you can of course write the menu in the same manner, so you can see and control it as I'm doing today. So I have using the ADC3, and I have the data register. So if I run my MCU and I turn the potentiometer, you see that the value will be updated in real time, and the debugger can read this. So this is also quite handy to get a live update, so to say. So if we put in a breakpoint at thread number 3, we will stop. If I hit Control B, I will see which breakpoints I have. So I can either disable them for now and then enable them later, or I can say kill all if I want to remove them. So I have a variable called tick, so I can add tick to a watch window, or I can have a look at the value of tick in the memory window. So if I run, I will see that tick will be updated accordingly. And if I stop, I can also go in and alter the value of tick. So because I have the debugger, I can read and write the memory as I wish. So this is also quite handy. So of course I get the call stack. So if I go to let's say here, and I run, I get the call stack of thread 1. So what thread 1 is actually doing, and if it has any local variables, it has I, which is equal to was equal to 31 hex. So this is also what you would expect from a debugger. Okay, so this is it for debugging, or debugging with level 1. So let's exit debug mode, and let's go ahead and turn on debug and trace level 2. So now I will be using the debug interface and the 1-pin trace interface. So I go debug, and I need an init file. So the init file has been written by Keil, and it's basically taking care of the multiplexing for the MCU. So the MCU will now produce level 2 debug and trace to my trace connector. I need to go into the settings, and I need to turn trace on. I see that I have in serial wire output mode, and I will enable ETM port number 31, so the RTOS is allowed to pass messages when the task switch is happening, and I have enabled port number 0. So in my case, I'm only using the printf function, so I will pass printf messages over the debugger to the debug window. I've also enabled the exception tracing. I click OK, and I enter debug mode again. So first of all, we can open a debug printf view window. So when I run, I will get these messages printed out here. I can go ahead and add the value to a logical analyzer. So if I would like to display a signal in real time, this is possible when I have the 1-pin trace interface. So I would like to go ahead and say ADC vol. So the value of the ADC, because it's a 12-bit, so then it can be between 0 and FFF, say close. So if I hit run, and if I turn the potentiometer, you will see that the signal is changing in real time. So this is also quite handy when I want to have a look at a behavior like this. Also, because I've enabled the ETM port 31, so the RTOS is now sending me messages when a task switch is happening. So if I zoom out a little bit, I get to see quite good. We can stop. I get to see very well how the RTOS is, how the tasks are switching, and when the different threads are happening and so on. So if I want, I can measure time as well in between. So if I measure the distance between two systicks, you see that the difference is 1 millisecond, and that's good because that's what I want. So this is also quite handy. Have a look at how they are calling each other and so on. We also get the exceptions. So if I have for the supervised call, I get the exceptions, and of course for the systicks. So I can get the numerical value for this as well, for the here. So then I only get like set numerical value of how many supervised calls and how many systicks have I had. Okay, that's good. So we can of course have a look at the trace data as well, but the trace data will show the ITM messages. So it will show me the various exceptions, so exception exit, return entry exit, and it will show me when the task switching has happened. So port 31, task number 3 is now executing. Okay, so this is what I can see when I have level 2 debug and trace. So let's go out of debug mode and let's turn on the instruction trace. So I go debug, ULINKpro, and I need a different initiation file. So trace port. I need the setup, and I need trace. So I say 4-pin trace, 4-bit data trace, and I say ETM trace enable. So here you have the option to choose unlimited trace. So if you would like to trace for a very, very long time, then you can have the debugger, you can stream the trace data to the debugger and then from the debugger to your hard drive. So then there is really no time limit. It's more or less the size of your hard drive that sets the limit of how long you can trace. We say OK, and we enter debug mode. So first of all, if we have a look in the, so we have, if we close this, so we have stopped at the first instruction of main, and if we have a look here, we see that the first instruction that we have traced is the beginning from the reset vector. So this means that you are able to do instruction trace from the very beginning of your MCU. So all of the resets, all of the setting up and such things you can do trace on. So we see which instructions has been executed, and we also get timestamps. We can of course choose to only look at high-level code, so only C code, but it's also like how you would like to display it. So if I run for a little bit and I click stop and I go to a thread, you will see that in a thread we have green here, which means that the code has been executed. We see that if we hover over a line, we see how many times this line has been executed, and we can also see the average. So we can even see this on the instruction level. So how much is average for each instruction? So this is gives us very good overview of how long all the different things take. So you also see that we have a line here which is gray, so this means that the line has not been executed. So this is due to the if statement. So we are checking if TID thread 3 is larger, if it's 0, then we should return -1. So we see that we have done the move and the load, and then we see that we have done the branch not 0. So we see this instruction was executed but never true. So therefore it has a different color. So this means that the if statement has been executed but not true. So this is very good when we would like to look at these types of things. We can also get a little bit more overview of the code coverage. So if I go here and I say update, and I have a look at thread number 3, I get, well, I see how much of each function has been executed. So 100% of thread 3, which is very good, but only 92% of init thread 3, and this is due to this if statement. So you see here one conditional jumps not fully executed. We can also have a look at the performance. So we can either have a look as in modules, so we can see for each C file how much time we are spending where, or we can have a look on functional level, so how much time we're spending in each function. So I see that I'm spending 45% in the OS idle daemon. So this means the load that I'm putting to my MCU is 55%. So it means I can put some more functionality to this system before I need to start thinking about switching to a more powerful MCU. Okay, so this is it for the debug and trace. I'm going to go over now to the event recorder. So first of all, event recorder. So the event recorder is a new feature, and it's done because in the past the software components were more or less black box for the application programmer. So you could sit there with your USB stack and you don't know why it's not working, but the only thing you know is that it's not working, and it's very hard to debug. So Keil has created the event recorder and the component viewer to make it easier for you to show the status and which code or events that has been executed by your component. So we have here, so let's show you the API. So the event recorder is a small piece of software that you need to add to your project, and it's in the menu here, so you just tick the box, and then you will get API, so functions which you can use. So you need to initialize the event recorder, you can start and stop it, and then you have 3 functions where you can pass messages to your buffer, to the event recorder buffer. So how is this working? So we need to do some instrumentation in the target software. So in this example, I have a function which is called receive complete, and it has an input parameter of size. So when this function is called, and if it's turned on, I will pass the event record to, so I will pass 2 words to the event recorder buffer. So event, my component, receive complete. This is the group of the message and the ID of the message. So it's a number, so it's just a define. It will pass the parameter of size, and then it will pass 0. So this will then be stored in the event buffer. So the event buffer, each data record has a timestamp, it has a data payload, and it has some meta flags. And then the event buffer will be read by the debugger. So once it has been read to the debugger and transported to the Microvision GUI, the events will be displayed. So if you have an XML file which provides the description for you, then you will get very detailed information on what is going on in your software. So for the MDK middleware, the event recorder, or there are events provided for you out of the box, and the XML file is also provided for you out of the box. So you don't need to do any any implementation here. It's just ready to run. I will show you this in a little while. So the benefits. So it works via standard JTAG or serial wire debug, so no trace is required. So this means it works with every Cortex-M device that's out there. Instrumentation code is time deterministic. So it takes around 340 cycles for the event record 2 to complete, and this is next to nothing for a modern Cortex-M device. The event recorder calls are non-blocking, which is very good, and the event recorder can be called from an interrupt service routine. So it's available with every debug unit, so from the simple baseline debugger to the high-end ULINKpro debugger, you can use the event recorder. It's also available for the third-party debuggers as well. So annotations can stay in production code, and if they are disabled, they consume 40 clock cycles, which is also next to nothing. So this is quite handy because the event recorder can be turned on and off during runtime. So this is not something you have to do in compile time. So at runtime, you can turn the event recorder on and off, and you can also filter the messages that you would like to look at. So if you, for instance, have a project where you have a USB stack and you have a IPv4 stack, so then you can filter out during runtime which messages you would like to look at. So if you're only interested in the USB stack, then you can filter away the messages from the IPv4 stack. So this is very handy. So therefore, the annotations can stay in production code, and if you were to find some nasty bug during late testing or even when your product is released, the events can be turned on by the debugger. There's also error detection by the debugger. So when you define the events, you can define the events as errors. So it will be quite clear where the errors are happening in your event recorder buffer. And as I said, available on every Cortex-M core. Create your own event. Okay, so we're gonna hold with that for a little bit. I'm gonna switch project and I will show you how this is looking. So I have a project which I've taken from the pack installer. So I'm using the USB device head. So first of all, when I enable the event recorder, I need to tick this box. So add the event recorder software to my project. And because I'm using the USB, I need to go to the library of the USB and I need to use the debug variant. We say cancel. So I need to configure my event recorder. So I have chosen to have 128 records in my event buffer. So the only time you need to go larger is if you notice that you will have a FIFO overrun in the event buffer. But bear in mind that the event recorder buffer is stored in your ROM, so this is consuming ROM. So each record is 16 bytes long. And then as a timestamp source, I'm using the DWT cycle counter, which is something you would never use in your application. So this is all I have to configure. And in my code, I need to add, of course, the event recorder header file, which provides me with the APIs. And then in main, I need to do event recorder initialize. And if you're a little bit uncertain what this function is doing, if you put the cursor here and you press F1, you will be taken to the documentation of the event recorder. I will say event record all, and then I will give 1 because I would like the events to start recording. So then I just need to set up the debugger. So I'm only using debug mode and no trace, as you can see here. I say OK, and I add this application to my target. So we see we have the event recorder window here. So if I step a little bit and I step over, I step out, so we see that an event was created, and if I hit run, you will see that multiple events have been created. So if I stop, you see that we have quite detailed, we have the time, so when did this event occur, we have who created the event, we have the event property, so a little bit on what the event is, and then we get the value. So things like this. So if you're interested in what each event means, you can click here and you will be taken to the documentation. So you will see what this event, for instance, is doing and what the different values mean. So we can have a look here in the filter. So I have now turned on all of the events. So let's say I'm only interested in the USB device. I'm not interested in the USB host, and I'm not interested in the STD.io. So let's remove those. Let's clear the event buffer, and let's run. So when I connect to the USB device 0, I see that some events were connected, and if I turn the LEDs on and off via the PC, you see that events here will be created. So this is actually quite handy to see and to really know what's happening in your component. We also have for the USB and device, and for all middleware component, we have a component view. So we can see the status of our component. So for device 0, we see that it's configured. We can see the assigned address, the number of interfaces, and so on. So this gives us kind of an overview of the status of our component and also how we have configured our component. So this is quite nice and all good, but you can of course use these type of event records in your own applications. You can create this by yourself. So I'm going to give you a small example of how this is done, and then I will show it quickly to you. So the event recorder is providing me with APIs. So I'm using a simple Blinky project which I created yesterday in webinar 1, where I turn one LED on, wait for half a second, and then turn it off. So when I turn the LED on, I have created a message with the event record to function. So the ID is A500, and this I've specified in an XML file. So there is a template for the XML file, and the only things I have written is these 2 lines here. So the ID of the event, the level is API, the level could be error instead. Property is what the event is about, and then I'm giving a value. So I can display this text, LED turned on. So which LED did I turn on? And then I choose value number 2, which is a define called LED 6. And then I see the result of the turning on of the LED. And this is value number 1, which I'm passing in. So this is quite simple. So I've written 2 lines of XML. So let me show you how this is working in practice. So I will switch project again. I say my project. So the thread I have is I turn LED 6 on, which is LED number 6. I pass the message to the event recorder, and then I wait for half a second. So to use this XML file, which I have created, I need to go to debug, and I need to go to manage component viewer description files. So we see here I have the default one from ARM. So this is what ARM has provided for me for the middleware components. And then I have my own, which I have written myself. Say OK, I say OK, and I enter debug mode. So if I hit run, you will see that the events will be passed to the event recorder, and you see that the LED will be blinking. So if we stop, we see that I get LED turned on equals 6 and result 0, so it was a success. I get a timestamp, and then I see that I have an event recorded every half a second, and this seems to be what I desired in my application. So I have the OS delay 500. So this is also validating that the timing I'm intending to use is working. So I think this is a really powerful way of giving annotations and passing messages to the debugger. So this is all I had to say for today.